Hey there. Yeah, got a haircut. But more importantly, I wanted to let you know that today's lecture is going to be on A/B testing and that it is a guest lecture. This lecture will be on the final, so drink it in. Sorry it has to be a video, but in this new strange world where there's barely any breathable air, that's just how we're doing things. But I'll see you next week, so in the meantime, await the rains to come and cleanse and restore our blasted and destroyed landscape. I will see you next week.
My name is Steve. I'm going to tell you today about randomized experiments, A/B tests, and sequential monitoring. I'm a PhD student in the stats department, like Fernando said. Before that, I was a software engineer here in the Bay Area for 7 years, and I ran a lot of A/B tests. And that's what got me really excited about statistics. And here I am. So I hope I can impart a little bit of that excitement today. And, all right, good. We'll start with my favorite game, Guess the Winner, and also an example of an A/B test. So this is this website, Dr. Foot Care, and you see here 2 images of a shopping cart page. And so people at this website wanted to test these 2 different versions of the shopping cart page and see which will get more people to buy stuff from the website. So if you're at this website and you want to test these 2 versions, what you're going to do, you're going to design these 2 versions of the page, then have visitors come to your web page, and every time they hit the shopping cart, you'll randomize whether they're going to see the left version or the right version, and then you're going to measure how many people see each version and how many people go on to make a purchase, and that's the basic idea behind an A/B test, to figure out which version is better. So I know this image is pretty fuzzy. That's what I've got from the paper, but you can look at it and see which one you think was better. It looks like it's a pretty subtle difference. It's not mostly the same layout, mostly the same colors and everything. But it turns out the one on the left was 10 times better. Actually, the one on the left here was the old one, and the one on the right was a new version that they rolled out, hoping to improve things, and it was a 90% drop in revenue for the company. And the culprit turned out to be this little enter coupon code box there. So people would come and check out, but then say, oh, coupon code, I don't have a coupon code. I better go find a coupon code. And then they go off searching, and then they're lost, and they forget about it. So 90% drop in revenue. Amazing that such a small difference has such a huge effect. But that's what happens with A/B testing sometimes, the exciting ones. Here's another one from a paper by the same lead author, a researcher at Microsoft, who I'm indebted to for all these examples. This is a widget from the MSN.com homepage, I believe, and it's a widget to direct users to real estate partner sites. And the top left was the original widget, and then they tested 5 variations. So again, you can look at those and see which one you think did the best. I thought maybe the top right with the little computer-generated image of a house catch people's eyes. But no, it was the one on the bottom right. 10% increase. Simplest one, just a little box to enter your city, state, or zip. So sometimes these things are unpredictable. And my last example, maybe some of you have heard of this, but this is from that same author, so this is an experiment run on Bing. And you hear sometimes about these search engines optimizing the colors and making millions more dollars. And, I thought it was crazy, but they actually published this. And so you can almost not even see the difference. It's so subtle on this projector, but it was a $10 million increase switching from the left colors to the right colors. Maybe if you download the slides afterwards, you'll see it better. So this stuff really does happen. All right, so now you've got some examples. And I like this quote from that same article about the color experiment. For years, Microsoft, like many other companies, had relied on expert designers rather than the behavior of actual users to define corporate style guides and colors. And I really like this because this gets to the heart of A/B testing. We like to believe that human expertise is the best way to design a product. We like to believe that, when we're designing products, that we have that genius insight. You have some new feature, it's your baby, and you create it, and you engineer it, and you bring it out there, and it's going to be so great. But you've got to be objective and test it against the users. That's the only way to find out. And that can actually be hard to do, to let it be objective. Okay, by the way, I should have said at the beginning, if you have questions, just interrupt me. I'm happy to answer questions. So what are we really doing with A/B testing? We want to know which version is better. It's a simple-sounding question. It's actually a very, very complicated question. What we'd really like to know is, well, in one possible universe, I could roll out the left version of the shopping cart page to all my users and see what happens. In some other universe, I could roll out the right version of my shopping cart page and see what happens. And I want to compare those two possible universes and see which one's better for my company. And of course, we can't do that. But maybe to see why this is so difficult, we can narrow the question down a bit and say, what if just you, one person, came to my web page and I could show you version A of the shopping cart, or I could show you version B of the shopping cart, and which one's going to be better, which one's going to get you to make a purchase? And if you think about this enough, you realize you really can't answer that question. Because I can only show you version A or show you version B. I can't show you both. I could show you version A and then version B. Then you've already seen version A, and it's not the same. Your experience is colored by that. So you can really never observe both outcomes, and thus you can never reliably answer this question. And this is sometimes called the fundamental problem of causal inference, that we can't observe these two outcomes and compare them. We can only observe one. And if you think about this hard enough, it becomes kind of amazing that we can answer these causal questions at all with experiments, but we do it so regularly these days we all take it for granted. So my take-home message for you is that carefully designed randomized controlled experiments are the only reliable way to learn what works best. Only reliable way. There are other ways. You can use existing data. You can try to control for confounders, fit a fancy model, but it's never as reliable as a randomized experiment, and it can go very wrong. And I put carefully designed here because I'm going to talk about some of those important design choices that you have to make, because randomized experiments can also go wrong if they're not designed well. Here's a nice quote from Fisher, very important early statistician, maybe you've heard of. Sometimes the only thing you can do with a poorly designed experiment is try to find out what it died of. This is something that you see a lot if you do the statistical consulting course and you have scientists coming in from around campus. They bring their experimental results to you that they've worked hard on for months, and now they say, well, what model should I fit? How should I analyze this? And the first question is, well, did you randomize? How did you randomize? And if they didn't randomize anything, it's tough. We can do an analysis and try, but there's no guarantees. There could always be confounding factors that we can't rule out. And it's just the saddest thing in the world, because if they'd taken the time to design and randomize properly up front, it would be simple to analyze. So it's important to think about this up front. So here are the three things we'll talk about today. We'll talk about why randomized experiments are so important. I know you've heard about this some already this semester, but I want to drill it home because it cannot be drilled home enough. Then we'll talk about a few key design choices when you're running an A/B test or randomized experiment. And then we'll talk about a little bit at the end sequential experimentation, which is my personal research interest, if we have time. And I didn't set a timer, so I'm just going to start one now. And do you know what are we at? 10 minutes in? All right. Oh, there's a clock in the back. Perfect. All right, great. Okay, so here's a very coarse-grained distinction of statistical problems. And as an example, let's just imagine hypothetically that we have data on birth weights over some time at a certain hospital and information about the mothers, including whether they smoked. I think this is maybe an example you're familiar with, I'm told. So here's a prediction problem. A new mother comes into the hospital. Can we predict the birth weight of the next baby based on some information about the mother, including whether or not she smoked? And for this kind of problem, this is what you'll learn about in a machine learning course typically. You can use any algorithm you want, random forest, deep learning, what have you, fancy models. And you just have a held-out data set, and you check your accuracy on that held-out set. And if your accuracy is very good on that held-out set, that's pretty much the end of the story. You've got a good predictive model. And in some sense, that's what makes prediction problems easier than the others we'll talk about. Once you've got a held-out set and you have good accuracy on that held-out set, that's the end of the story. Of course, there are wrinkles. The future observations might be different from the past, and some people in the machine learning field do definitely think about that. And also don't mean to dismiss the prediction problem as easy. It's very hard and complicated and fascinating. But it's different from, say, an estimation problem, where now we're saying, what's the difference in birth weight between smokers and non-smokers in the population that these mothers were drawn from in the data set that we have? And importantly, how precise is that estimate of the difference? For something like this, you might construct a confidence interval. Confidence interval involves probability statements. Now we need a probability model. Now we need to think about how our data were sampled from the larger population. So things are getting more complicated. But still harder, I claim, is a causal inference problem, which is, for example, what will be the effect on the birth weight of babies if I tell the mothers to stop smoking, if I tell the smokers to stop smoking? And you start to think about this, you realize you just can't answer this from the data that you have, because you've never told a smoking mother to stop smoking. There are no mothers in your existing data set where you told them to stop smoking and saw what happened. So you just don't know what happens unless you go out there and tell mothers to stop smoking. You can compare the mothers who smoke to the mothers who don't, but of course they may differ in other ways. They may differ in their diet, alcohol consumption, other things that could affect birth weight, and so you can't rule out the fact that those explain the difference in not smoking. This is just the association is not causation phrase that we're all familiar with, but it always seems to creep up. So I like to always bring it up. And so what we really need is two groups of mothers, one who is smoking, one who we told to not smoke, who are otherwise similar. They differ only in the way that we treated them. We told one to stop smoking, we didn't tell the other group. That's what we need, these two comparable groups, and that's what randomized assignment gives us. When we randomize each mother to receive this treatment, telling them to stop smoking or not, then we get two groups comparable except for the treatment. And that leads us to the first benefit of randomization, which is freedom from bias. And I love this quote from Fisher: designing an experiment is like gambling with the devil. Only a random strategy can defeat all his betting systems. So when you're designing an experiment and you think, well, we can control for that, or I have a good model for this, just always remember you're gambling with the devil, and he or she will find a way to defeat your system and introduce bias, unless you randomize, and then you can't be beaten, on average. Okay, I'm going to show two tables from Friedman, Bassani, and Perv, Statistics, a book that I'm sure you all know and love as much as I do. And this first table here is looking at 51 studies on this particular medical treatment, and they're categorized in the columns here by the degree of enthusiasm for whether the treatment was beneficial, whether it was effective. And the top row shows studies without any controls. The middle row shows studies with controls but not randomized, so we're comparing patients who received this treatment to patients who didn't, but there was not randomized assignment. And then finally, in the bottom row, you see the randomized controlled trials, the ones that I'm telling you should use. And we might expect, if we make this table, to see, well, the ones without randomization were a little bit more biased in favor, and the ones with randomization a little bit less. But the difference is just so marked. It's so distinct. It's amazing to me. There's just such clear enthusiasm for this treatment among trials that were not randomized, and among those that were randomized, just completely on the other side. So it's just a perfect example. If you don't randomize, your biases will creep in, usually in the direction of confirming what you already want to be true. And this is a great example. And here's another one, looking at 4 different medical treatments now. And they're categorized again by plus if they were positive about the value of the treatment, minus if they were negative. And you see the randomized controlled versus historically controlled, which is where we just take some patients that received the treatment, compare them to some patients in the past who didn't receive the treatment, maybe before the treatment was available. It seems like a good idea. You might think the patients in the past were completely comparable, but you see here they're just not. And bias creeps in. And again, the difference is just amazing, how overwhelmingly positive the historically controlled studies are and overwhelmingly negative the randomized controlled trials are. An interesting and kind of sad story about this one is that this bottom row, DES, was a drug given to women in the 60s to prevent spontaneous miscarriages. And you see these historically controlled studies that showed that it worked. They did some randomized studies. They showed no benefit. Doctors ignored that and kept prescribing it. And then later, I think in the late 60s or early 70s, studies came out that it actually increases risk of cancer in the child 20 years later, and it was banned in 1971. So it can be dangerous to ignore the randomized experiments. So that's the first benefit, which is this freedom from bias. There is the second benefit, which I know Professor Stark talked to you about not too long ago, which is that randomization gives us this reasoned basis for inference. By putting a known randomness into the world, we are randomizing patients with some mechanism that we know about, some random number generator that we're running. And by putting that randomness into the world, we can justify probability calculations based on that randomness. So this idea goes back to Fisher. It was also called putting a rabbit into the hat, as I know Professor Stark talked about, by David Friedman. And without putting randomness into the world, you're allowed to assume some randomness by positing a model. And those models always rely on assumptions that are difficult to check and can really lead you astray. And so I remind you of this quote from Box Hunter and Hunter: don't fall in love with a model. It may be very mathematically complicated, maybe mathematically elegant, it may be very plausible, but it can lead you astray. That does it for that first section on the need for randomized experiments. Any questions at this point? Okay. Yeah.
Isn't there a cost to randomizing experiments? Show people random stuff. So like, I might lose money.
Yes. There can be a few costs. One is that it's easier to just grab some data that's out there already, like in the Kaiser example with the mothers and birth weights. To randomize, you actually have to go out there and randomize and set up a randomization system and set up a protocol. But I think you're referring to, like when I have the 2 checkout pages, if one of them is really bad and I'm randomizing half my visitors to see this really bad page, you could be losing a lot. So to some degree, if you think this new page is going to be good, you have to try it and see. But what you'd like to do is, as soon as you have enough evidence to see that this page is bad, I'm losing money, I want to stop and not show users that page anymore. And that's actually this third point, sequential experimentation, being able to stop early. Same thing comes up in clinical trials. If you're giving patients a drug and it seems to be having harm, you want to stop as early as possible. So we'll talk a bit about that. Yeah.
One other thing is, one strategy you could do is if you're concerned about a new website or a new page not working, you could just do maybe like a 1%, 99% split.
Mm-hmm.
And then as you see that it's not emerging revenue, you could raise it up to 10, 20, up to 50.
Yeah. So, what's your name?
Jake.
So Jake here points out that another strategy, if you're worried about a new treatment, maybe losing a lot of money in the website example, is that you don't have to randomize 50% of your visitors to the control and 50% to the new treatment. If you have a lot of traffic, you could randomize 99% to see the control and just 1% of visitors to see the new treatment. So you can set that treatment ratio, and if you're just sending 1% of traffic and then you run this for long enough to see that, okay, this page isn't terrible and it's not losing tons of money, then you could ramp up the ratio of people that you're sending to the new treatment. And that summarizes it well. Yeah, and maybe you might ask, well, why not just send 1% of the people in the first place? Why ramp it up at all? And the answer is power, which we will talk about shortly. All right. So first, choosing the unit of randomization. The A/B test examples I've talked about so far involve just randomizing each user to see one version or the other, and we sort of take that for granted as the default, but it's not the only choice. So our example here, let's think about a pricing experiment. And this graph here is from one of these Amazon price trackers that maybe you've seen. So this is like the price graph for a Bluetooth smart lock, I think, over the last 3 months. And it's just all over the place. You know, here in mid-March, we're down to $160, then $190 a few days later, and then $230 one day. People who bought that day were really unlucky. And back down to $190, back down to $160. And if you think about it, it's kind of crazy that Amazon can do this and get away with it. Most companies, if they knew that you were moving price around like this, people would be up in arms. But they're Amazon, so I guess they can do whatever they want. But if you were running a company, and you might want to experiment on pricing, because that's one of the most important levers you have to affect your business, how would you do it? It's a tough question. So one thing is you can randomize by session. What's a session? A session is when you open up your browser and you go to some website. That's one session. The browser can keep track of everything you do within that session. You can go to other places, come back to that website. They know you're in the same session. You close your browser. Session's over. Next time you come, it's a new session. So I'm not going to get too much into the details of web programming, but it's good to know what a session is because that comes up all the time in A/B testing. So you can randomize by session, but now you can see this has an obvious problem that someone could see 2 different prices right after one another, or they could have their computer and their phone open and be seeing 2 different prices side by side. And that user might get pretty upset. You, in general, don't want to make your users too upset. So maybe instead we'll randomize by user. If we have some unique user ID, we can randomize users into maybe the bucket seeing the lower prices, the bucket seeing the higher prices. This would solve that problem of the user seeing 2 different prices at once. But you could still have me and my friend sitting side by side, opening up the same page and seeing 2 different prices. And again, users might get upset. Also, you might feel that's a little bit unethical to charge one person something and another person a higher price for the same thing at the same time. And it is important to think about ethics when you're running experiments in the real world on real people. So maybe we don't want to run it randomized by user. Maybe a creative idea is randomized by product instead. So each product in our large catalog of products will randomize to bump the price up a little bit or down a little bit, and then try to measure the effects of price changes that way. That might work. Might still have some issues. Maybe you have 2 closely related substitute products, like 2 brands of toilet paper, and you bump the price of one up, bump the price of the other down. People might just shift from buying one brand to the other because they don't really care about the brand. They just want to buy the lowest price. So you might not really be getting the effects of what would happen if you were to raise prices across the board or lower prices across the board. Maybe you think, okay, let's randomize by product category. If you're a website like Amazon, you probably got thousands of categories if you go all the way down the product category tree. And so maybe we'll just randomize a whole category to get a price bump up or down. And that would solve this problem we just talked about. Maybe now you don't have a whole lot of categories. So that's an idea. Another crazy idea, maybe you could randomize by day. Each day you flip a coin and you bump all your prices up that day or bump them down that day, and then you try to track what happens. Of course, these days aren't independent of one another, and if someone sees a higher price one day, it could affect their behavior the next day. And so you've got this dependence problem. I don't have a good answer for you here. Sometimes, the point is there's just not an easy answer sometimes to the right unit of randomization. And this can be really tough, but you need to think about it. You shouldn't just default to randomizing users in every experiment. But what I can tell you is whatever unit you randomize on, you want to analyze on the same unit. So if you do an experiment where you randomize by product category, then you want to compute one summary outcome per product category, and you want to compare those outcomes when you do your analysis. And what this implies is that the effective sample size of your experiment is the number of randomized units. So if you have 50 categories on your website and 1,000 products within those categories, if you've randomized the 50 categories, then you essentially have 50 units in your randomized experiment. You don't have 1,000 units. And so the alternative to this is to analyze at a finer grain level than you randomized at. So you might randomize by product category, but then analyze by individual products. Another example, if you're doing, say, TV advertising, and you want to know if the TV advertising actually works, you can't show TV ads to individual users on individual TVs. You can only choose which cities or media markets you get to show your TV ads in. So you might randomly pick some cities to show your TV ads in and leave them off of the rest as controls. But then your cities are the units, and you have to analyze an average outcome for each city rather than analyzing individual users. If you want to analyze the individual users, it can be done. It's often called cluster randomization, but then you have to introduce modeling assumptions. Your calculations will no longer be justified purely by the randomization. It'll depend on some model. And to try to illustrate this point, there's an extreme example where maybe we just have two cities, and we're going to randomize one city to see TV ads and the other city not. So we have just San Francisco and Los Angeles. Now in my randomization, there's only two possible randomizations I can do. Either I show ads in San Francisco or I show ads in Los Angeles. I'm just flipping one coin. And that means in the distribution justified by the randomization alone, there's just two outcomes. The outcome if I show ads in San Francisco or the outcome if I show ads in Los Angeles. And so I know you've talked about doing simulation-based p-values where you simulate all the possible outcomes. In this case, there's just two outcomes, and there's really not a lot of information for looking for extreme outcomes or for generating p-values. The alternative, of course, is to take all the individual people and treat their outcomes as random. Maybe each individual person, there's some overall average, and there's a normal distribution around that, and then the treatment effect adds some offset. You can introduce these modeling assumptions, and you can get whatever conclusions you want, but those modeling assumptions are not justified by the randomization. Okay. Second point is about choosing who to enroll in your experiment. To talk about this, we need to talk about power, as promised. So why do we use hypothesis tests at all? Why do we use statistics? Well, in this case, hypothesis test gives us a guarantee against making false discoveries. So if the treatment has no effect, the chance of making a false discovery is at most 5%. That's the guarantee that using hypothesis test gives us. That's why we use them. But it's easy to make a hypothesis test that satisfies this guarantee. Here's a hypothesis test. Never declare a discovery. There. Now your chance of false discovery is 0. But of course it's a useless test. So we need some other guarantee. This isn't enough. So we need a guarantee when the treatment does have an effect. And we want a guarantee that looks like this. If the treatment has at least a 20% lift, so lift refers to the relative improvement that a treatment has on some outcome. So if we're looking at that shopping cart example and we want to know the percentage of people who see the shopping cart who actually go on to make a purchase, then if that's 10% of people and we make a change and that raises it to 12%, that's a 20% lift. Another common term in A/B testing. So the guarantee we want here is that the treatment has at least a 20% lift, then the chance of detecting it is at least 80%. So this is the second guarantee, that if the treatment is at least so strong, we will detect it with a high chance, a high probability. And the way we're going to get this guarantee is with sample size planning or power calculations. And to do sample size planning, we need these three numbers I've shown here. The first one, the 5% chance of making a false discovery. That's called the type 1 error rate in the lingo, although I often just refer to it as the chance of making a false discovery. The second number here, this 20% lift, that's our minimum planned for effect size. There's many terms for this out there, but I like to call it the minimum planned for effect size because that's the effect that you're planning for, that you're going to have a guarantee at. If the effect is stronger than that, you just get even better guarantees. If the effect is weaker than that, you won't reach your power guarantee. And then finally, the 80% there is called power. That's your chance of detecting the effect if it's at least this strong. So we take these three numbers, and we plug them into some function. And so this is a Python function. There isn't actually a Python function out there in the common libraries to do power calculation for comparing two proportions. So I wrote one, and I will work with Jake to post an IPython notebook. I mean a Jupyter notebook with this code, and I'll send a pull request to stats models, so maybe it'll be there by the time you need it. But this 0.1 here, that's the conversion rate or the rate of people going on to complete a purchase in the control group. That's actually not one of the three numbers that we talked about. That's something you should estimate from historical data. It doesn't have to be perfect. It should be in the right ballpark. So this is saying if there's a 10% conversion rate in the control treatment, get the control bucket, and then my new treatment has 10% times 1.2 conversion rate, so that's my 20% lift. And I'm running at a significance level of 5%. That's that type 1 error rate, or the chance of a false discovery. And I want 80% power. Then this function will tell you the sample size you need. This is the number of subjects you need per group. So we need something like 7,600 people total. And the idea is that we run this calculation before we run the experiment. Then we run the experiment, and we run to 7,600 people. And then we can stop, compute a p-value, compare it to 5%. If it's below, we declare a discovery. And we have both of these guarantees we talked about. So that's sample size planning. That's power calculation. This power calculation assumes that you're splitting people evenly between the two groups. If you're sending, as Jake mentioned earlier, just 1% of people to one of the groups, you're going to need more people. An easy rule of thumb is that the smaller group needs to have this number. So if you're sending 1% of people to the treatment group, you need to wait until 1% of your visitors equals 3,800 people. So that's a lot more than 7,600. Okay, now we've got power calculation down. Yes? No problem.
Do you have information on variance of whatever outcome you're looking at? Is that something you would also want to include in the power calculation?
If you have information on variance of the outcome you're looking at.
Like, for example, if you're tracking spend and you know how spread out the amount of spend is.
Okay, yeah, that's a good question. So the example I've shown here. Yes, thank you. If you have information about the outcome you're looking at, for example, if you're tracking spend, so here we're tracking just a 1-0 outcome of whether you converted or not. But if you're tracking spend, like how much money the customer actually spent, which is a numerical outcome, and you have some information about it beforehand, like how spread out that is, what the variability, maybe what the standard deviation of that is in historical data, would that enter into your power calculation? And the answer is yes, definitely. What I've shown here is power calculation for comparing two proportions. So because the outcomes are just 0, 1 valued, all you need to know is the proportion, like 10%, and then you also know its variability. When you have something like dollars spent, if I tell you the average dollar spent was 100, it could be like ranging from 90 to 110, or it could be ranging from 0 to 1,000 with some skewed distribution. And so you need information about the variability. So there will be a separate function that you will use, which actually does exist in the stats models library, to do a power calculation based on this numerical outcome. And that will take into account the variability. You'll have to put in the variance or standard deviation of your outcome, which, again, doesn't need to be perfect, but you should guess it from historical data. Okay, thank you. Okay, now we've got power calculation. We can talk about who to enroll in the experiment. And my first point is to randomize lazily. It's always great when the teacher says you should be lazy about something, so I like this. So to talk about this, we're going to imagine we have this funnel up top here. Funnels are very common in A/B testing, so if you're going to do it, get used to looking at them and look at them a lot. So we imagine we have 50,000 visitors a week coming to our website. of those 50,000, 1% advanced to the checkout page. And then of those 1% advancing to the checkout page, then 20% actually complete the purchase. So this is a funnel. And now we imagine that the variation, we're going to do a test on the checkout page, and the variation we're going to introduce, we imagine maybe it increases conversion rate from 20% to 25%. That's going to be our minimum planned for effect, is a 25% lift in this case, from 20% to 25%. Okay, the simple idea and the bad idea is to enroll all visitors in your experiment. So every time a visitor comes to your web page, you immediately randomize which version of the checkout page they're going to see when they eventually get there, and you record that in your database, which bucket they've been placed in. And that means that the total conversion rate that you're looking at is 20% times 1% of all the visitors, compared to 25% of 1%. And those are very small proportions, and so this power calculation says we need 280,000 visitors, so a lot of visitors. Okay, a better idea is to wait until visitors actually get to the checkout page. 99% of people never see the checkout page. They never see this treatment that you're applying. So wait till people actually get to the checkout page and have an opportunity to see your treatment, and then randomize them at that moment to see one version or the other and record that in your database and show it to them. Now, the effective conversion rates that we're looking at in our experiment are just 20% versus 25%, and we need only 2,200 visitors at checkout, which is a much smaller number. But of course, this is visitors at checkout, and so it's not a fair comparison. This was total number of visitors. So we have to multiply it by 100 to account for that 1% drop-off in the beginning, getting to checkout. But we do that, and that means we need 220,000 visitors in this case, which is still a 20% decrease in the necessary sample size. So the important thing here was we got this completely for free. We didn't have to give anything up. All we had to do is be a little bit smart about how we randomize, and in particular, randomize at the last possible moment. The idea being that people who are never going to see your treatment are just dead weight in your experimental sample. Okay. Here's an example where we get something not for free. So say treatment is expensive. So far I've been talking about we just have two versions of a web page and we just randomly show one version or the other. And that's free. We can just show that to as many people as we want. We're not having to pay anything to do that. But sometimes treatment might be expensive. Like someone gets to your checkout page and you say, hey, if you go ahead and complete your purchase, we'll send you a $5 Starbucks gift card. This has been done and known to have effects. And in this case, of course, you have to pay per treatment. So treatment is now expensive, and so imagine, like before, among all users at checkout, 20% complete the purchase, but maybe we know there's some subgroup, like among people with 2 items in their cart, when they get to checkout, 40% complete the purchase. It's plausible. Okay, so the first idea is, like before, just enroll everyone, and we need 2,200 visitors, just like before, at the checkout page. Of course, the people getting to the checkout page are the ones we have to offer the Starbucks gift card, so those are the ones we're paying for. And the second idea is only to enroll the people who have 2 items. This is going to be a smaller group of people, but they have this larger conversion rate. And under the same lift here, a 25% lift, the power calculation says we need only 770 visitors now at checkout. So a 65% decrease in the required sample size because we chose a group that had a larger baseline conversion rate. And again, this might be great if the treatment is expensive. If the treatment is not expensive, we might not have actually decreased our total sample size in terms of total visitors to the website, because it might only be very few visitors who actually have 2 items in the cart. Yeah?
This will affect our conclusions. We can no longer say that all visitors that are at checkout who are given a gift card will have improvement.
Yes. So it's Joey, right? Yeah. Joey points out that this affects our conclusions because we can no longer say that all visitors who arrive at checkout are affected by the treatment in this way, and this is a critical point. So we've no longer gotten something for free. We've gotten something by giving something up. And so I want to talk about these 2 key terms, internal validity and external validity. Internal validity means, can I draw conclusions that are valid for the subjects I looked at in my study? So in this example, have I made a correct conclusion about whether the treatment has an effect on those visitors with 2 items in their cart? And because those visitors have a higher baseline conversion rate, and it's easier to detect that effect, we might have higher internal validity. We'll be more accurate in making a statement about the effect of the treatment on that group. But we can only make a statement about users who have 2 items in their cart. We can no longer reliably say that the same effect will be seen for all users, including users with 1 item in their cart. And that's called external validity. Do the conclusions of my study generalized to the wider population. This is something you'll see a lot in medical studies, like clinical trials. If you have some drug that's supposed to lower cholesterol and help heart health, you'll generally enroll people who have really high cholesterol and bad heart health because those are the people you're going to see an effect on. But then when you draw conclusions, you can really only say that your conclusions apply to people with high cholesterol. You can't say that it applies to the general healthy population. So this can be a difficult trade-off sometimes between internal and external validity, but worth keeping in mind. That external validity jump does not come for free. Okay. My last design choice I want to talk about is choosing an outcome metric. My example here will be a search quality experiment. So here you see screenshots of two leading search engines. These are two different search engines, although they look very similar. And on the left side here, well, on both sides, I have searched for Python power calculation. I think it's hopefully somewhat legible. And on the left side here, I searched for Python power calculation. The first result was the Python math standard library, which has a math.pow function for raising a number to a power. It's one thing power calculation can mean. And then we've got something about experimental design, power analysis. This one you can't see. Is there a Python function to determine parameters for power in an experiment? The answer is no. And so that's what we were just talking about, power calculation. On the right-hand side, I search for power calculation. I've got Stack Overflow thread about calculating a power for decimal, so taking a number to a power. I even get a code snippet right up front for that. Then taking numbers to a power again, the star operator, and then a link about making a calculator in Python. So two very different sets of results for the same query here. And if I really was searching for how to take a decimal to a power, then this result is great. I've got a code snippet right there. If I was searching for power calculation for experiments like we've talked about, these results are much better. So this is a tough example in search quality. The query is a little vague, and it's not clear what the best results are. So if you're working at a search engine, working on the search quality team, and you want to run an experiment, you've got some change to the algorithm. You want to run an experiment. Every time a user or a query comes to the site every time a query comes in, you can randomize which algorithm you use to choose the search results, and you can show those, and that's fine, a randomized experiment. And now we can measure which set of results did better. But the question is, how are we going to measure which set of results did better? It's a really tough question. How do you measure search quality? So we need a metric. With any experiment, we need a metric. We need a single number that we can use to measure how good the outcome was for each of the two different versions. So in this example, this is an example taken from that same researcher at Microsoft that I'm taking all my examples from. We'd like to improve market share. And so market share we might think of as the number of queries sent to our search engine, say in a month, divided by the number of queries to all search engines out there. And this is a key number we'd like to improve. But of course we can't measure the denominator, so maybe we'll just use the numerator as a proxy. And so these authors from Microsoft report this experiment. There was a bug in the experiment, and so it showed very, very poor search results. And yet they saw a 10% lift in queries per user, one of their key metrics, and they saw a 30% lift in revenue. And this is like an amazing, huge change. And they went and checked it. Usually when you see these kind of things, you think, oh, it's an error in the tracking or in the analysis or something. But they double and triple checked it. It was a real effect. So what's going on here? How do these bad results have this amazing effect? Well, if you go to a search engine, type in a query, and you get terrible results, what's the first thing you do? You type another query. I type Python power calculation, I don't get what I want. Maybe I try Python statistical power calculation. And so people would just start sending more queries to find what they wanted. And so this bad change had a very positive effect on this key metric because the metric wasn't capturing what they wanted. And likewise, most search results pages have some paid ads at the top and then the so-called organic results below that. And if the organic results, those are the ones affected by the search relevance function, if those get very bad, the ads look relatively more relevant and more useful. So you get more clicks on the ads, make a lot more money in the short term. In the long term, people will stop using your search engine. So you need to make sure your metric captures the right thing. This can be tricky. So here's a little bit more detail about this case, which I think is interesting as a kind of case study. You can take this raw queries metric and break it down this way. Users you see per month times the sessions per user. Remember, we talked about sessions, how many times a user is coming back to the site, times the number of queries entered per session. And the number of users is essentially fixed by design. If you're randomizing half the people to see one version, half the people to see the other version, then you're going to have the same number of users in each bucket. So that's not helpful. And this last one, queries per session, that's the one essentially we were just looking at that's really tough to interpret. If it goes up, is that a good thing or is that a bad thing? It's really no way to know. This middle one, number of sessions per user, how many times each user came back to the site during the experiment, that's the one that they said they thought was the best proxy for search quality here. One of them. They say it's a key element of the overall criteria for evaluating search quality. And it makes sense. If users are having a good experience, they'll come back to the search engine more. This was Bing in this example. Doesn't seem perfect to me. I don't know what you all think. But the fact of the matter is, in a lot of experiments, there's no perfect outcome metric. And so you have to make compromises and think carefully about it. But the important thing is if you pick the wrong metric, you can be actively encouraging bad changes. And that's the example we saw here. Now, this question always comes up, well, maybe I have multiple outcome metrics that I care about, and I just want to look at all of them and see what happened. And my advice is you can't just blindly look at all of them. You should pick one metric, one number that you're going to use to measure the difference between the two treatments and to do a statistical test and make a decision. And this is often in the lingo of the industry called a key performance indicator, or KPI. So when you do an internship and someone throws that term out, you can just nod and be like, yep, I got that. So pick one primary metric. If there are others, and they're really important, and you need to look at multiple metrics to make a decision, you need to correct for multiple testing. Unfortunately, I don't have time to talk about multiple testing, about correcting for multiplicity, but there's lots of resources out there to learn about it, and you need to make sure you learn about it. If you just look at lots of outcomes and choose the one with the lowest p-value, you can exaggerate your findings. There are ways to correct for that. And now my last bit of advice, which is maybe controversial, but if those other metrics aren't critical for decision making, of course you're going to measure them and you're going to look at them, and that's okay, but educate yourself about multiple testing and educate your coworkers about multiple testing, or your fellow scientists as it may be, so that you're aware of making faulty conclusions. And I believe that's it for my 3 design choices. Any questions on that? Okay. Oh, there. Sorry. Yeah. Yeah. The question is, am I interested in looking at natural experiments, like with historical data where you can't control all this? So natural experiments refers to when you have some data gathered already where randomization did not go on, but maybe you think there's some mechanism so that it's as if there was randomization. My favorite example, I think we got time. I'll tell this. Love this example. John Snow was a doctor in the 19th century, I think, in England, and cholera was a big problem. He was trying to figure out what was going on with cholera. This is from both of Friedman's books, I think, and a paper of his. And people didn't have germ theory yet. I hope my dates aren't off. 18th century, 19th, anyone know? All right, we got a few 17th, but mostly 18th. I'm going to go with 18th. And, okay. And trying to figure out what's going on with cholera. And so one thing he did was, as we know now, cholera, is very important that you're getting clean water. There's germs. People didn't know it was germs at the time. They had this miasma theory that it was like odors or something and came from dead bodies. And so to solve that problem, they would dig up dead bodies and take them and throw them in the river, which is a really bad idea, turns out. But he did this study where there were 2 companies in London that would bring water from the river to people's homes, and it wasn't like this chunk of the company has this chunk of the city comes from this company, and this chunk of the city gets water from this company. They were intertwined. We're on the same street. This house might get water from company A, but this house gets water from company B. And this infrastructure went back a long time, and people had moved, so people might not even know what company they got their water from. And so he felt that which company you got your water from was as if random. You just moved into a house, and which house you got, he had this quote about it was equal between the rich and the poor, and so on. So he thought it was as if random. And so this is sometimes considered the first natural experiment, where what happened is one of the water companies decided to move their intake up the river to a cleaner part of the river. And so all of a sudden, a sort of as if random half of the city started getting cleaner water. And so Jon Snow went door to door, asking people, knocking on houses, asking people, have there been any cholera deaths here? Is it cholera? Is that the right one? Yeah. And asking people, have there been any cholera deaths here? And recorded thousands of data points and showed very conclusively that the people in the homes where the company had moved the intake to a cleaner part of the river had much, much lower incidence of cholera. So pretty cool. So that's that is a not randomized, but as if randomized, we like to say, or a natural experiment. And I am interested in that. And there's a lot of research going on in the field of causal inference on sort of natural experiments. And there are varying degrees of quality of research. And natural experiments can range from very low quality to almost as high quality as a randomized experiment. But it's always dangerous because you can't know for sure that there was some confounding factor that you just didn't know about. It's that gambling with the devil quote. So it's definitely worth learning about, but it's not as high quality as a randomized experiment. Anytime you can do a randomized experiment, you should. Certainly when you're restricted to looking at historical data only, you can't go back in time and randomize. So then you'd want to learn about natural experiments. So that was a short answer and then a long prelude to explain, but did that answer the question at all? Okay. Yeah, doing analysis of natural experiments is just complicated. Okay. All right. So, what was that?
1854.
Left.
Jon Snow.
Oh, 1854. Got it. So it was 18 minutes and 54 seconds. I was like, that's very precise. Yeah, 1854. Okay. 19th century then.
Yep.
All right. Yeah.
Study of natural experiments is actually a pretty big area. And I don't think we have any classes on it, but there are some really good books on how to set up experiments, how to analyze data using instrumental experimental design or other techniques to deal with data sets that have already been collected. And they have limitations, but it's an area that people do study.
Yeah.
So, close to the piazza, actually.
Okay, yeah, Joey was saying that there is a big area of study on natural experiments, sometimes called quasi-experimental methods, I think, and he will post some links on Piazza, maybe. There is a course, Stat C 239, which Jazz Seekon teaches. It's like definitely a higher level stats course, but if any of you are ambitious and really excited, you could go for that. I don't know if there's other courses. Okay. Okay, now we get to talk about sequential experimentation, my favorite topic. I hope this will be fun. How could it not be fun? Let's talk about random walks. So, we're going to play a game. We're going to imagine playing a game many times. And this game is simple and involves flipping a coin, which is my favorite kind of game. And so every day for 1 year, I'm going to flip a fair coin. It's really fair. And if it's heads, you'll pay me $1. And if it's tails, I'll pay you $1. And we'll just do that every day for a year. Simple game. It's a fair game because it's a fair coin, obviously. On average, no one's ahead, no one's behind. On average, we're both even. So now the question is, what's the chance that after the first 8 days of the year, one of us pulls ahead and stays ahead the entire rest of the year? The entire remaining 357 days of the year, one of us stays ahead. So I've got these 4 choices. And I'm only asking you to guess to within the order of magnitude, so shouldn't be too hard. And I think, yes, there's a link. Does the link show what the answers are? Or should I pull that back up? Oh, perfect. Okay, perfect. Perfect. Okay. Sure. It's exciting watching these come in live.
Popcorn in the microwave.
Yeah. It is like popcorn. Keep thinking it's done, and then a few more pops come in. Okay. Is that about the right amount of time? The popcorn is slowing down here. Okay, sure. Yeah. Wish we could show it. It's pretty cool. We have 18% of people saying 1 in 10, another 18% of people saying 1 in 100, 33% of people saying 1 in 1,000. That seems to be the popular answer. And then 29% of people saying 1 in 10,000. So what have we got? 62% of people, 62% of people saying 1 in 10,000 or 1 in 1,000. Pretty unlikely outcome. The right answer is 1 in 10. So 1 in 10 chance that one of us pulls ahead in the first 8 days and stays ahead the entire rest of the year. It's crazy, right? I'm glad that that wasn't the most popular answer because it really surprised me, and I was like, what if everyone else thinks it's obvious? Yeah, of course I didn't believe this either. So I ran a simulation, what any self-respecting statistician would do. And so here's one path of my profit or loss over the course of a year. So 365 flips, and I start at 0, and then each flip I go up 1 or I go down 1. And so it's what's called a simple symmetric random walk, where each step I just go up 1 or down 1, each with probability a half. And this walk is kind of what I think we imagine most walks look like. It just kind of wanders around 0 because it's a fair game. No one's expected to win or lose in expectation. And it kind of crosses a few times. But this is just one path. Let's look at 100. There's 100 paths superimposed. And the green ones, I've highlighted the ones where one or the other player pulls ahead and stays ahead the entire rest of the year after the first 8 days. You can look at those paths and see that they're ahead basically the entire time that you can see in the plot. It's reasonably visible. And so in this case, there were 100 walks in this plot, and exactly 10 of them had this property. So the theoretical probability is like 10.3%, I think, and worked out really well. There's a related property, which is not that I pull ahead for the last 357 days, but just that any 357 days out of the year I'm ahead. So I could be ahead and then fall behind for a day, then be ahead again, then fall behind another day. But 357 days of the year at least, I was ahead. So just looking at the amount of time I was ahead or you were ahead, one of us was ahead 357 days out of the year. The probability of that's actually exactly double the probability of what we just saw. It's like 20.6% theoretically. In this case, 15 walks out of 100. So we can go a step further, and we can just say for each path, I'm just going to look at the number of days I was ahead and do that for many paths and plot a histogram. So here's that histogram for 1,000 walks. And we know it has to be symmetric because it's a fair game. We can interchange my roll and your roll, and the game doesn't change. But we might imagine, like most symmetric distributions, we see that it kind of peaks around the middle It peaks around us just being even, ahead half the time, behind half the time, and then falls off. But it's the opposite. The most common value is just I'm ahead the whole year or I'm behind the whole year. It's pretty crazy. And what's even crazier about this is that all these probabilities can be computed with essentially elementary calculations. A lot of really clever tricks, but elementary calculations. And these are called arcsine laws. You can find the limiting distribution with a simple closed form. So I'm not going to go into the details, but this is really cool, and you can read about it. I got it from William Feller's old book, An Introduction to Probability. But it's covered in many places. The take-home message I want here is that our intuition doesn't really apply very well to random walks necessarily. We have this intuition about long-run behavior, about things averaging out, and certainly the average number of heads that I've seen should converge to 50% of the time. And that's kind of the law of large numbers, or the central limit theorem tells us about the fact that it should look that way in long runs and how much it'd be spread around that. But when we look at path properties of random walks, like how many days I'm ahead in a row, then there's a lot of correlation between days of the random walk. There's a lot of dependence, and that kind of breaks our intuitions. And so if you run an A/B test, as one lesson from this, if you run an A/B test, and you see that one treatment pulls ahead and stays ahead for days in a row, you might think, well, that's really solid evidence, strong evidence that this variation is better. But it's not necessarily, because there's just these path properties of random walks, that can happen by chance pretty often. Good thing to keep in mind. Maybe a more practical example, next time you're watching the Warriors game, and they pull ahead in the beginning and stay ahead the whole time, and all your friends are saying, oh, the Warriors are so great, the other team didn't stand a chance, they were behind the whole game. You can say, well, actually, properties of random walks, even if it was an even game, you might have expected one team to pull ahead and stay ahead the whole game, and then that will make you really popular in the room, I guarantee. Okay, so that's random walks, that's fun. And now let's talk about repeated looks. So our last important lesson about A/B testing, repeatedly looking. Here's a screenshot of the dashboard for a popular A/B testing platform, commercial A/B testing platform out there called Optimizely. So one thing I haven't talked about today, and I'm not going to talk about, is the mechanics, the actual engineering of running a test, of randomizing and tracking all these users. That's a whole hard topic of its own, getting good data tracking. But Optimizely wants to take all that out of your hands. So platforms like this, if you want to run this A/B test, you put a bit of Optimizely's code on your page that tells it to randomize and what the two versions of the page look like. And then every time a visitor comes to the page, Optimizely will take care of randomizing them to one version or the other, showing them the right version, recording how many people have seen each version, and how many people have converted in each of those buckets, which is what you see here. You have all the raw data. This particular test has 3 variations, not just one, against the control, or what they call the baseline. And you see this plot of conversion rates over time, and you can see the raw conversion rates. And then what you see in the right column here is what they call chance to beat baseline, which is 1 minus a p-value. And so you can watch that column, wait for that number to go above 95%, i.e. for the p-value to drop below 0.05, and you can be refreshing this page every day or every hour if you're bored sitting at work. And then you can stop the test as soon as you get that result and declare a winner. And that's what a lot of people do at many companies, but it's not a good idea. It's not a good idea because by refreshing this page every day, you can inflate your error rate. Your chance of false discovery can go up. So let's explore that more. Say we have a coin, because I love coins, and we want to determine if this coin is fair. Maybe this is the coin that we're going to play the game with for the next year, and you want to check it. So what would you do? You start flipping it. And maybe you flip it and get tails, heads, tails. That doesn't really tell you anything, of course. Flip it a few more times. Now, starting to be a lot of heads, but maybe you're not quite convinced, not really enough data. So you're going to flip it a few more times, and you start to quickly realize we don't really need to keep track of all the heads and tails. What I need to know is how many heads there were out of how many total flips. So in this case, 24 flips, 15 heads. If the coin were fair, I'd expect maybe 12 heads on average out of 24 flips. I saw 15, so it was a bit high, but how high was it? Was it surprising? Was it unlikely for a fair coin? And that's exactly what p-values are for. Okay. So going back to that guarantee that we talked about, the guarantee of hypothesis test, if the treatment has no effect, in this case if the coin is fair, then the chance of false discovery is at most 5%. This is what p-values are giving us, because p-values have this key property. If the treatment has no effect, the probability that your p-value is below 0.05 is no more than 5%. And so that way, if I run the test, compute a p-value, and declare a discovery when the p-value is below 0.05, then my chance of making a false discovery when there's really no effect is at most 5%. This is what's so great about p-values, is we can use them to control the chance of false discovery. I think this is probably familiar, but a quick review. Let's look at some p-values from simulations with a fair coin. So here I've simulated a path with a fair coin, and what I'm doing is that each time I'm computing a p-value based on the flips so far, a p-value for whether the coin is fair. And what we see is if we wait until 215 flips, like we got out of our sample size calculation, say our power calculation, and we compute a p-value, and here it's around 0.04 maybe, and that's pretty high, so we're not going to conclude the coin is biased, which is good because it's not. It's 0.4. Did I say 0.04? 0.4, so very high. And thank you. And that's good. But what I've shown here is not just the one p-value, if you wait till the right sample size, but a whole path of p-values computed after every flip. And you can see that there's this excursion down to low values early on. And if I were to watch the p-values continuously and stop as soon as it drops below 0.05, I could stop the test here, declare the coin to be biased, which would be a false discovery because it's not biased, it's fair. So this is just one path. Let's look at 200 such paths overlaid, and they kind of make this big mess of blue. But what we see is if we wait until 215 flips and compute a p-value, most of those p-values lie above 0.05. Only a few of them lie below 0.05. And so with this fair coin, if we wait till 215, compute a p-value, and declare a discovery it's below 0.05, the chance of a false discovery is low. But that's not what we're talking about doing. We're talking about watching it continuously and stopping as soon as the p-value drops below 0.05. And now there's lots of these paths that cross 0.05 at some point, and we stop the test and declare a discovery. In this case, I had 200 simulated paths. 35% of them reach significance at some point. So 35% of them now, with this fair coin, we're declaring that the coin is biased. So our chance of false discovery has gone from 5% up to 35%, which is very bad. We've completely lost the guarantee. And you might be wondering, well, how bad can this get? And the answer is, as bad as you want it to be. So here's a plot just showing if we keep flipping the coin, monitoring the p-value, stopping as soon as it drops below 0.05, what's the chance of a false discovery? And we were just looking somewhere around here, a few hundred. You can see if you go up to 100,000, then we're up above a chance of false discovery of a half. And if you keep flipping the coin, you can make this go as close to 1 as you want. So with enough coin flips, you can be certain of declaring that the fair coin is actually biased. So this is the danger of continuous monitoring. And I want to quickly point out that this is not limited to A/B testing. This is related to Joey's question earlier, but I brought up that when you're running a clinical trial and you have a drug, if it's doing a lot of harm, has unexpected side effects, you want to stop the trial as soon as possible and not harm people. On the other hand, if the drug is very effective in saving lives, you want to stop the trial and give it to everyone so you can save more lives. So clinical trials use sequential monitoring. This is where a lot of the original work on sequential monitoring came from. And in lab experiments, if your experiment involves doing some crazy treatment to some mouse, you don't want to have to treat too many mice, so you maybe will treat them in batches. This is an example that my collaborator Aditya brought up. Someone in the audience at one of his talks mentioned. Do this experiment on 10 mice, run the analysis, see if you've got significance. No? Okay. Go do an experiment on another 10 mice, add that into your data set, see if you've got significance, and so on. That's sequential monitoring, and that will invalidate your conclusions, potentially. Okay. So the last bit, what can we do about this? And so I want to talk about, if we have time to get through it, maybe a way to compute p-values based on simulations, as you've been learning about this semester, in a way that's valid for sequential monitoring. So here's what I hope is a review. If I want to compute a p-value for whether a coin is fair, well, what I'm going to do, say, is flip the coin 1,000 times and compute this t-obs, my test statistic, which is going to be the number of heads minus the number of tails after 1,000 flips. With a fair coin, I expect that to be, on average, equal to 0, so centered around 0. And in order to figure out what its spread is, I'll just simulate many times 1,000 flips of a fair coin on the computer, compute this test statistic, T1000, make a histogram, there it is, compare my value of T-obs, and look at how often I got a value larger than that. That'll be my p-value. And so, for example, here, if I had 70 more heads than tails, I might get a p-value of 0.03, roughly. Okay, So now we want to be able to monitor sequentially. So in this case, we're not going to monitor continuously, but we're going to say after every 100 flips, we want to be able to compute a p-value and maybe stop the test early. So it's 1,000 total flips, but we're going to look 10 times after every 100 flips. So now we have a sequence of test statistics. T1000, the number of heads minus the number of tails after 100 flips. T200, the number of heads minus tails after 200 flips, and so on. So a sequence of 10 test statistics. Okay, a real quick probability calculation. For each of these n's, for a fair coin, Tn is a sum of independent, identically distributed random variables, each taking value plus or minus 1. Because it's the number of heads minus the number of tails, so for each flip, I either add 1 if it was a heads or subtract 1 if it was a tails. So it's plus 1 or minus 1, each with probability a half. The variance of that plus minus 1 random variable is 1. Its mean is 0. Its difference from the mean is always equal to 1. So the squared difference is always equal to 1. Now Tn, which is a sum of n such variables, independent, identically distributed, is going to have variance n times 1. So variance n, standard deviation is square root of n. And so if I want to standardize these test statistics and get them all on the same scale, all having the same variance, I'll divide by square root of n. I do Tn divided by square root of n, and the variance becomes 1 for all of my test statistics. And this is, I think, somewhat familiar, I'm told. And let's look at a picture to illustrate it. So here I've simulated these paths of these Tn statistics after 100 flips, 200 flips, and so on. And this is just the number of heads minus the number of tails. And you can see it spreading out over time because the variance is growing. The standard deviation is growing like square root of n. And so it's way more spread out over here than it is over here. But if instead I look at Tn divided by the square root of n, then I standardize them. Now it's not spreading out anymore. They're just all on the same scale. So I've put them all on the same scale. So that's the first step. I've got the standardized test statistic. Now I've got the sequence of standardized test statistics. And what I'm going to do is form a new test statistic, which is the maximum of all 10 of them. I'm going to call that T star 1000. It's going to be the maximum of all 10 of my standardized test statistics. And I can simulate that. And so I can just use that in the same procedure as before. So what I'm going to be able to do is after every 100 flips, I compute this standardized number of heads minus number of tails. This is for n is 100, and then n is 200. And then at each n, I compute the maximum of all these standardized test statistics I've seen so far. That's my little T star. And now I can simulate this big T star, the maximum over all 10 looks, simulate that many times to compute a p-value just like before. So let me show you that histogram, that helpful picture. Here, this histogram shows the simulated values of that big T star, the maximum standardized test statistic over 10 looks, from 100, 200, up to 1,000. And remember before that these were centered at 0, because each test statistic is equal to 0 on average. But now we're not looking at a single test statistic, we're taking the maximum of 10. And that gives us larger values on average. That's the whole problem with sequential monitoring. We're looking for a big value. So we're going to get larger values. So these simulated values of T star are not centered at 0. It's shifted up. And that's what can give us invalid inference. But since we're simulating these values with that selection of the maximum 1 now, we can correct for that. And so what we're going to do is at each stage, n equals 100 and then n equals 200, we'll compute our little T star, compare it to this histogram of simulated maximal test statistics, and compute a p-value in the same way as before. And in this simulation, what we have is that if little T star was equal to 70, just the same value as before, we standardize it, we put it into this histogram, and we get a p-value of 0.05, a little bigger than 0.05. Remember, it was 0.03 before. Now it's gotten bigger. So we've corrected for that sequential looking. And so this is sort of repeating what I've said. But now we can compute a p-value after every 100 flips using this method. And we can look at it after every 100 flips, stop as soon as it drops below 0.05. And we still have this guarantee we wanted that if the coin is fair, the probability that any of the p-values we compute is below 0.05 is no more than 5%. So we can look repeatedly, and we still get our error control, our guarantee that the chance of false discovery is no more than 5%. On the other hand, if the coin is biased, then we have a chance to stop early. We don't have to go all the way to 1,000 flips. We won't be able to stop after 200 or 300 flips and then not waste time. And two things to remember about this procedure is we do need to choose the maximum sample size ahead of time. That was 1,000 in this example. You can't run to 1,000 and say, oh, we haven't got significance yet. I want to run new simulations with a maximum of 10,000. You can't do that. You do have to pick a maximum ahead of time, or you can inflate your type 1 error rate. And then we can only look as often as we do in the simulation. So if the simulated p-values involve looking at a test statistic after every 100 flips, you can only look after every 100 flips. You can't look after every flip and compare that p-value to this simulated distribution. So you need to still follow those two rules. Otherwise, you can still invalidate your guarantees. So this is just one method for computing, for doing sequential monitoring, which I think hopefully fits in with what you've learned in this course. There are lots of other ways, and maybe you'll get excited about it and learn more. Then you'll be like me. Okay. Any questions on the sequential monitoring, sequential analysis part? That's it for that. If I don't see you raising your hand, you can just yell out. Oh, yeah. Can I ground the last section with an example? We did get a little bit abstract there. Let's see. I think an example would be maybe what illustrates it is that screenshot I showed, where we could imagine that these are variations on that shopping cart page that we saw at the very beginning of the talk. And so we roll out those, say, 4 different versions of the shopping cart page, and we're tracking how many visitors see each version and how many of those visitors actually went on to make a purchase. And so that gives us, for each version of the shopping cart page, this conversion rate, which we're measuring. And this graph is showing that conversion rate over time. So this might have been after day 1, things look like this. And we wanted to look at the results at the end of day 1, and let me say after week 1, the results look like this. And the reason I say that is because you shouldn't really run a test for just a day. You should run it for at least a week, because behavior on the weekend can be very different from behavior on Wednesday. And if you stop the test after just running it on a Saturday, you could get results that don't apply to the other days of the week. Not a point I talked about, but let's say this was after the first week, and we're looking at these results, and the gray one here, which I don't know which one that is, maybe the baseline looks the best, and we might be tempted to stop the experiment then. And then maybe this is after week 2, and now the gray one's really looking good. But we can kind of see that this was partially just random chance. And if we're sort of watching after every week, stopping as soon as we get a strong result, that could bias our results, because we're stopping as soon as we see sort of random chance making one variation look good. And so we might keep looking after week 3, after week 4, after week 5. And what this sequential p-values method gives you is a way to be able to look after every week, but not fall prey to this danger that we just stop as soon as we get, just some random noise. I don't know if that helped clarify at all. Joey has something.
This happens a lot. As if you work with engineers, they will look at their charts and go, oh, we're definitely winning now. And so this chasing the lift game is something that, as a data scientist, you often have to push back and say, we don't have enough evidence yet. You can't just keep looking at the chart and say, your new system is better. You need to actually run the experiment. You need to compensate for the fact you are looking at it.
Yeah, so Joey says that this happens a lot where engineers will be watching a graph like this and saying, oh, yes, we're definitely ahead. We have strong evidence. Our new version is winning. This goes back to that confirmation bias we talked about. You want your new version to win. You built it. You're excited about it. And as a data scientist, he's saying often you have to push back and say, no, we don't have enough evidence yet. We have to wait. And that's all part of the fun, exciting life of being a data scientist, pushing back constantly people's intuitions. Okay. So I just will wrap up. Summarize what we've talked about. We talked about randomized experiments, about randomizing treatment, why it's so important, protects you from bias, number 1. It also justifies probability calculations. We talked about planning the experiment, making design choices before you run the experiment. You should carefully choose the unit of randomization. Make sure that the unit of analysis matches the unit of randomization for the safest and most rigidly justified conclusions. Think about the enrolled population and the effects that has on power. And think about the outcome metric and whether that actually measures what you care about or whether you're encouraging bad changes. And then finally, if you want to monitor sequentially, and there's nothing wrong with that, you should want to monitor sequentially, of course, but make sure you use sequentially valid methods. And I've given you one example, and I think Jake and I are going to work on a Jupyter notebook showing some of those calculations, so you can play with that. I put the sources there if you want to download the slides. Thank you so much. And thank you to the teaching staff for giving me the opportunity to speak to you.
Thanks, Steve.
Yeah.
Appreciate it. It was awesome.
Thanks.
Wonderful. I really enjoyed it.